structural experts advising ancient New Zealand on area of practice gardens. Cool. Thanks, Harry.
Thanks, Cam, and I recently became Vice President of SESOC as well, so yeah, a few things going on. Look, here today to talk about the Majestic Centre Seismic Strengthening Project in Wellington, a project that was completed about 2 years ago. So I've presented this in several forums, but invited to do a bit of a lecture series around New Zealand by NZSEE recently. So here today in Wellington on Thursday, and then down in Christchurch next month. So really privileged to be able to do that. So a little bit of history, context and what we'll talk about today. So a little bit of context to start, a bit of history about Majestic Centre. I'll give an overview of the strengthening that was undertaken, including the timeline and the process that we went through in undertaking that. Talk about some of the key structural features and challenges of the project, and as part of that, I want to talk a little bit about some of the lessons we learnt along the way, and I think there's a lot of lessons for this building in particular around new building design and not repeating some of the mistakes of the past, and then I'll touch on some of the outcomes towards the end. So just a little bit about Wellington. I think I don't need to dwell on that. We all know where we live in New Zealand, Pacific Ring of Fire and lots of faults in and around the Wellington region. And with the Wellington fault in particular running really close to the CBD in Wellington, just a K or so away from the Majestic Centre itself. The building itself is on Willis Street, site of the old Majestic Theatre. The theatre was closed in the mid-80s because it was earthquake prone. And it was demolished to make way for the construction of the Majestic Centre itself, which was designed through the late 80s and constructed in the early 90s. And that's a photo there of it being built. It was kind of one of the last big buildings at the end of the construction boom in the 80s to be completed, and had a bit of a checkered history through its construction as well, but I won't talk about that today. So a little bit about the background and timeline of our involvement. After the Christchurch earthquakes back in 2011, we got asked by Kiwi Property, the owner of the building, to undertake an initial seismic assessment. So we did that through the mid part of 2011. We initially found a few issues as part of our initial seismic assessment, gave it a rating of about 50% MBS, there or thereabouts, which kind of asked more questions than it gave answers, I think, and so we kind of moved into a detailed seismic assessment phase, found some significant problems, and then flowed into a design process. And so the design process happened over the course of a number of years, with construction cascading through that period as well. So part of the premise of us getting involved and getting into this project was to actually make some early gains and improvements for the building, and so we had a staged and fast-track process to get on site, get some construction moving and get some improvements made to the building as soon as we could. Through the process we had some earthquakes through mid-2013, Cook Strait, the Seddon and Lake Grasmere earthquakes in Cook Strait during that time. They weren't massive in the context of the building capacity, but they gave everyone a bit of a wake-up call in Wellington and heightened the need to get on and do this project. And then just right at the very end, after we'd done the vast majority of the construction work, we had the Kaikoura quake. So again, thankfully, we'd done the work and the building came through that unscathed, so the client was very happy. Again, and sort of touched on this before, so sort of June 2011, we did a qualitative initial seismic assessment as part of a wider portfolio review for Kiwi Property, gave the building about a 50% MBS rating and recommended that a detailed seismic assessment was undertaken. Kiwi Property kind of sat on that while they were looking at other buildings in their portfolio, but came back to us a couple of months later to get underway with the detailed seismic assessment. We started doing that using modal response spectra assessment and analysis using ETABS, and got a few surprises. So found that the transfer beam in particular at level 5, this thing coming through here, which I'll talk about quite a bit later, had some reasonably serious issues, potentially earthquake prone, and recommended we do a more sophisticated analysis to actually get a better understanding of the load displacement and time dependent issues associated with the building. And so we managed through that process to convince ourselves that the building wasn't earthquake prone. It's at kind of below 50% MBS, but above an earthquake prone threshold. But that led us to recommend prompt strengthening, and the client was keen to get on and do that as soon as they could. So at that point, a project team was put together. We were involved, so the Kiwi Property were the client, and we were involved directly with them right from the get-go, but they got the Building Intelligence Group involved as project managers, ourselves doing structural, fire and some regulatory consulting work. I won't kind of mention everyone, but Becca involved with peer review, Opus and as architects, and a Stevenson Turner and a team doing building services, and TNT Geotech and Fletcher were brought on fairly early as the main contractor as well. And so we said it was really important to get a good contractor on board. It was going to be, we could see right from the get-go, it was going to be a very challenging and difficult project, lots of temporary works and phasing and sequencing challenges, and so we wanted Fletcher's on board to be part of the team developing the solutions right from the get-go. The whole strengthening philosophy from Kiwi Property was, initially it wasn't to achieve 100%, but that became 100% MBS imperative as we got into the project, and so we did that using a performance-based approach to ASCE 41, and so we looked at 100% life safety and 150% collapse prevention criteria as part of achieving that. It was really important for Kiwi to maintain the tenants in the building through the course of the work, so we did the whole project with the tenants still in the building, and so we had to maintain their quiet enjoyment and carry out the works in a fully tenanted building, and that drove huge logistical challenges for Fletcher Construction, but we achieved that. It was fast-tracked and staged, so we wanted to get on and get some stuff going on quickly at the start of the project, but there were discrete packages of work that we could stage through the duration of the project. So we worked on the tower first and then finished some of the podium stuff right at the end of the project. They wanted to get on and start construction as early as they could. Kiwi were keen for some meaningful interim improvement targets, so they wanted to be able to say, well, we've done some work now, so our percent MBS has increased, and so that kind of led to us tackling the transfer beam and the foundation for the shear core first. And all up, we had over 28 structural building consent packages, and I'm not sure how many overall building consent packages, but there were a lot more than that, a lot of them were non-structural, but a lot of building consent packages and a lot of information flowing throughout the course of the project. So a little bit about the building structure itself. It's a reinforced concrete building with a dual system. So the plan here, it's got a perimeter ductile concrete moment resisting frame, and then a central shear core. So these red elements here are back-to-back C-shaped shear walls with the perimeter concrete moment resisting frame. So it's a dual wall frame system. As you can see, it's irregular in plan, so it's got a curved side to the south. It's got this sort of faceted and rectilinear grid to the north. The perimeter frame transfers out at above the lobby level lobby level. So we talk about the level 5 transfer beam, which is this element through here. And so every second perimeter column transfers out at this level, and we'll get into that a bit further down the track. So that transfer structure created a few issues. It had a mixed foundation system, so piles, bowed piles under the perimeter frame, but pads under the shear cores. Again, a little bit unusual. It had a precast hollow core flooring system, and it had a mixed facade. So it's got a glazed curtain wall around the curved portion and a precast panel system around the north side. So it had a bit of everything going on. And in particular, it had stiffness, changes in stiffness, both vertical and plane. So it had transfers for the gravity system, and also the dual system frame and wall meant the system fights against each other in elevation as well, and we'll talk about that a bit later as well. So a summary of the strengthening, what's going on there. Foundations for the shear cores, the tower shear walls themselves, we looked at confinement and strengthening of them. Level 5 transfer beam, which I've talked about. The floors, so both tower diaphragms needed significant work, and restraint and support of precast flooring units. A lot of the hollow core issues that have been uncovered in recent times, we had to deal with that. Precast cladding was an issue, and then podium works as well, which aren't included as part of the presentation, but also became quite a significant part of the project. So by podium, I mean all the stuff out at the front of the building. There was quite a bit of strengthening work associated with that, particularly the roof and the big barrel vault roof that forms the main atrium. I'm not going to talk about that today. We're just going to focus on the work we did in the tower itself. So starting from the start, foundations. One thing we noticed really early on was these foundations under the shear wall, so 28-storey high shear cores through here. A lot of the gravity load lands on these internal C-shaped shear walls, and they all land down on quite small pad foundations on the rock. There's also these foundations had these associated cuts, so a sloping site, and we were quite worried about slip circle type failures. Those pads were very small, and the bearing pressures underneath them were really high. And then also through geotech work, it was found that the quality of the soils were fairly good rock down at this end, but got worse as you came back up the slope, because there was a very faulted and shattered sequence of rock down in this end of the site, and so the differential displacements you'd get on that pad compared to this one were quite considerable. So concerns about differential displacement of those pad foundations. And so the solution to all that was that we needed to kind of significantly improve this foundation system, and ended up casting a very large post-tension reinforced concrete pad system kind of to encapsulate all of that. A 2-storey high concrete pad in this void space, so didn't lose any car parking area in there. Lost a few car parks up the back here, but nothing that significant, to provide a toe to stop that slip circle sort of issue, to provide a lot greater bearing area, and to tie this system up together. We also installed a bunch of mini piles down this side to deal with the fact that we had poorer soils as you came up the slope, and we wanted to make sure we balanced the stiffness from one side of that foundation system to the other. So that in itself was a big job. There was limited access. There was a lot of material needed to be pulled out. There was load limits on the car park ramps that came in and out of that space, so everything was kind of brought in and out on a 2-ton pickup truck almost. And as you can see there, quite a bit going on in terms of forming up and casting those foundation elements. Moving on, the shear cores themselves and the actual walls themselves. Another kind of thing that was fairly obvious fairly early on was there was quite a difference in the detailing of the perimeter concrete frame to these shear cores. And so this C-shaped wall here is the only vertical element that inside kind of that half of the building. So a lot of the gravity load of the system lands on that flange. It supports this beam here and supports a big tributary area of floor in and around here. And so that element looks a lot like this column out here in terms of dimensions and area, yet this column was a very well-detailed ductile moment frame system, lots of, plenty of vertical reinforcing, so not huge volumes of vertical reinforcing, but getting up towards 1%, and very good stirruping, so tightly spaced sets of stirruping, well confined, looks a lot like a modern reinforced concrete column, where this flange had almost a third less vertical reinforcing, very low levels of vertical reinforcing, and very light stirruping and virtually no stirruping through big sections of the wall. So a bit of stirruping at the very toe, a little bit around here, and then no cross links or stirruping in the rest of the wall, and fairly low levels of shear reinforcing as well. So, really lightly reinforced concrete section, and we knew from experience in Christchurch that those sorts of systems don't perform that well. So one of the guys in the office came up with these series of slides of what kind of might happen, and I remember thinking at the time, is this really kind of what we could expect in a decent shake? As he was drawing these, and they kind of looked reasonably ominous and maybe kind of over-egging it in terms of our communication back to the client, and then we compared them to some of the wall failures we'd found in Canterbury, and it looked very similar. This type of failure to what happened in our own office as part of the Canterbury earthquake, and this is Hotel Grand Chancellor and other wall failures here were very similar to what we were predicting could happen to those shear cores in Majestic. And so there was a number of problems that we had to address as part of that. They didn't have enough vertical reinforcing, so we needed to add vertical flexural reinforcing, and we did that by putting a series of angles here and here. So these elements at the leading edges and at the back of the web, we needed to confine those flanges all the way up the building, and then we needed in some sections to add shear reinforcing and some confinement to the webs as well. And so we looked at various other options. We looked at FRP, we looked at various configurations of plating, but we came back to this. It's kind of like a full metal jacket almost, and this is what it looked like on site. Lots of drilling of holes, lots of plating, but this is what it needed to be a well-confined system with enough vertical flexural, external flexural reinforcing to deal with the demands that we were talking about. And this was a really kind of clear demonstration about a very literal interpretation of codes of the day. Kind of seemed to suggest that if you had plenty of axial load on a wall, you didn't need much flexural reinforcing, but Christchurch and more modern experiences has shown that not to be the case. Moving on to the level 5 transfer beam, so sort of have talked about that. So that's this element that comes round above the double height lobby. So this element here originally was a 2 metre deep transfer beam supporting about 20 floors of column that transfers out. So every second column, so this column here, doesn't continue down, transfers out with this transfer beam to these larger mega columns that come down through the lobby. And our early analysis showed that that transfer beam was way underdone, and in fact, inspecting that beam, we found some reasonably significant shear cracking in it already to show that it was definitely working, it was doing something, and you know, that kind of was reasonably alarming, and we needed to get on and do something about that. And so our analysis showed that that was failing at quite low levels of load, and the original premise with the original design was that the Verendale action from the frame up above would take about 50% of that transfer load, and the transfer beam would take the remaining 50%. But what actually happened when you get hinges forming in the frame above, that you get a progressive ratcheting down of that load, and so that load ends up being taken fully on this, and there's also a stiffness compatibility, so actually right from the get-go that probably takes most of the load anyway, and so that original design premise was found to not kind of work, and you end up getting all the load essentially landing on the transfer beam. The other thing, in order for this frame to be effective in doing its job to help resist the lateral load of the building, needed this transfer beam to remain elastic. So as soon as you lost this transfer beam, the moment resisting frame up above became a lot less effective in resisting the lateral load of the building. So, you know, fairly quickly found that the transfer beam had a very crucial role to play in the overall performance of the building. So what did we do? Again, looked at various options of how we might go about strengthening this, but the one that we keep coming back to was just adding to the depth of that. We didn't have any problem with the impact that had on the columns. There was plenty of headroom. It was up above a double height space, and so there was plenty of room to get in there and add significant depth to this transfer beam, and so the greeny coloured element there all the way around is the reinforced concrete transfer beam that we added to the existing transfer beam. We didn't have to do it through this section because there was no transfer going on through the front portion. We had to analyse that and figure out where the load was going and what portion of the load was taken by the existing beam versus what portion would be taken by the new beam, and that wasn't that easy. So a very complex strut and tie design and methodology was adopted, considering both the existing and future stress states. So all the gravity load was already in the existing beam, but we needed the composite section to take the future seismic demands. We also wanted that system to act compositely and have moment continuity through the column. And one thing that we found, you know, these columns were really well detailed. They were full of reinforcing. They also were holding lots of gravity load, so we couldn't effectively drill through those to pass reinforcing bars to get this flexural continuity of that bottom steel. So we had to go round them. So we adopted this system where these flexural bars actually passed in plan around the side of the column, and then we used a strut and tie system to strut back into the rear face of the column, but had to tie across here to complete that load path. So horizontal post-tensioning across this element to strut those loads into the back face of the column, and vertical post-tensioning up the side of that beam, clamped over with a header plate at the top to clamp those two beams together to make sure they acted compositely. And that was pretty tricky. I've got some photos to show that. But the other thing we were having to deal with was the fact that around the curved portion of the building there was also a big torsion imposed on this transfer beam, because you've got the load coming down this column here. It's offset from the columns below, and so you've got this twist, and that twist was quite significant, equivalent to a double-decker London bus 15 metres away. And so we had to deal with that twist, and we really struggled to figure out how we were going to deal with that, and we ended up coming up with this idea of a horizontal truss up high, resisted by a horizontal reaction on the base of that element down the bottom. And that truss component was and twist was really tricky to deal with. And so some photos during construction, this is one of the photos of the transfer beam along the northern straight face, this element that comes down the side of the existing columns, and these are some of these the caps to the horizontal post-tension rods that go across that bottom section of it. And then these anchor blocks are the ones at the top that cap off the vertical post-tensioning that clamps the two together vertically. Tricky, really tricky, construction-wise. Continuing to move on, so core tie. Another problem that I mentioned previously was the dual nature of the system, so perimeter concrete frame and then central shear cores. But the deflection profile of a shear wall versus a frame is quite different, and so you get this fighting of the two systems, and from one level to another, quite different transfer forces in and out of the diaphragm depending on where you are in the building. So down lower, you might get the cores going one way and the frame fighting against it itself in the other direction, but up high, the opposite thing is happening. So you're continually fighting these transfer forces in and out of the diaphragm up the height of the building. And we resolved them using, again, a strut and tie methodology, using some of the existing elements, so these beams that come across the building, and struts and ties that came across this way, and this was our strut and tie analysis representation of this kind of system on the plan of the building. But what we found is these forces got really big, so 3,500 kilonewtons at some levels trying to come in and out of this diaphragm here, and the existing building only had 4 D16 bars going from the end of these shear cores into the floor diaphragm. So woefully inadequate tie into those webs of the C-shaped shear walls, and just that was going to tear itself apart when you got these big transfers happening in a decent shape. So what did we do about that? We came up with this idea that we would have these tie plates that got fixed down into the floor topping, coming out from the end of each shear core. We put a fuse into them so that we knew that we would start stretching this fuse before we popped all the anchors that were going into the reasonably thin concrete topping. But then we had to somehow anchor that onto the end of the wall itself. And so we decided we'd clamp these back to back. So it's a little bit hard to see here. So we had an anchor block on one side and another anchor block on the other side. So this thing here is a representation of one anchor block. And then we post-tensioned them to each other. So we had these big anchor blocks that we post-tensioned either side of the web of the shear wall with post-tensioning rods passing along the outside of the wall either side. And so these big anchor blocks, just sit in there, and then this tie plate got welded to them. And so, a resolution of forces here, you get a tension on here that wants to pop up, so you crank a moment in here, but we could deal with that through this anchor block, take the tension force along here, and then strut back down into the shear wall. And again, that's what it looked like on site. So these big anchor blocks here, quite a detailed fabricated steel element. That's before they've got the post-tensioning cables going through them, and this is with the tensioning cables, and then they were tensioned onto the end of those. And this is the plate that runs across the floor with lots of little fixings going into the floor topping. What happened at the bottom though was that we had perimeter frames having plastic hinges at each end, and you get frame elongation in all of those perimeter frames. But at the bottom you've got a transfer beam that we wanted to remain elastic, and so you get these perimeter frames growing, but this one not growing because it's not hinging, and so you get this collection of transfers accumulating as you come down, and so much larger transfers happening at the bottom, which led to for the need for a much larger core tie and transfer system at the lowest level diaphragms. And so, you know, some big engineering going on there, really grunty stuff. Touched on the idea of frame elongation when you get plastic hinging and perimeter moment frames, and we've seen all of this particularly after Canterbury earthquake, but also after the Kaikoura earthquake. The Stats building had quite significant frame elongation in Wellington. That's what led to floors falling out of it. And so this stuff is real, and when you get ductile moment resisting frames hinging, they grow in length, so you get these kind of tears happening in floor systems, and we normally deal with them with conventional seating brackets, and so that's all okay in these corners. These movements aren't too bad and you can generally deal with that, but what we found, if you accumulate all those plastic hinges around this curved frame here and tally up the amount of frame elongation you might get, you actually end up with a really big displacement, and then when the building's moving up and down, that displacement kind of might bulge out one way or the other. So we spent a lot of time, and this was a lot of conversations with the peer reviewer around what would happen if we got this sort of crack happening, which we'd seen on other buildings on this curved frame, and the fact that we could get up to 250 millimetres of displacement of the frame away from the building, and would that lead to instability of the building or not? We managed to prove that it wouldn't, and the way we dealt with that was just some really big catch frames. So really big fabricated catch frames for the floor units, recognising the fact that in a really big quake maybe we could get separation of that curved frame, but the floors wouldn't fall down if we had big enough catch frames to catch them. So more conventional kind of 150 or 100 or 150 angles on other parts of the flooring system, but these really big fabricated ones around the curved frame. Dealing with other issues around Dycore floors with alpha slab issues where the bottom of the hollow core floor might split and fail, and so there was certain vulnerabilities in certain parts of the floor plate where that could happen next to the shear walls and next to the external perimeter frame, and so we came up with solutions like this to catch them on the way down. Essentially, we weren't trying to prevent that from happening, but we were just trying to deal with the consequences if it did. Precast cladding systems as well. We found that there was virtually no movement provision in the precast cladding. So we had to deal with the fact that we'll get interstory displacement, so you need some slot or some movement in the precast cladding systems. You might also get frame elongation, so that if the frame's growing, you know, you have to have movement in the bottom and the top system. And we decided it was going to be too hard to cut those systems off and provide slotted holes. What we'd do is just make a more resilient connection at the bottom and then provide some tethers at the top. So if they did pop, we'd catch them on the way down. And we put a kind of a fuse in this system so that we wouldn't break the rope before we started yielding this fuse in the catch bracket. We wanted to make sure that we didn't create a kind of day-by-day weatherproofing problem with trying to refix these panels in solving a kind of once in a 500-year seismic problem. So kind of that's the project. it kind of doesn't do justice to the scale and the complexity of it, but you know, some of the numbers might start to allude to that. So lots of concrete, lots of reinforcing steel, lots of structural steel, huge amount of man hours invested into this project, not only from a design perspective, but you know, the work that Fletcher's did on site was amazing. And then through this, we were also able to incorporate a refurbishment of the building. So the building was 25 years old. So on the way back through, after they'd done all the structural work, there was some new corporate fit-outs, a refresh of the building. The building was re-tenanted, or existing tenants renewed their leases through this process, and the building was given a real refresh and a new lease of life. So you know, so that was one of the really positive outcomes of this redevelopment. Was it was more than just a seismic strengthening project. So again, some of the outcomes, you know, a resilient building at 100% MBS. It was undamaged through the Kaikoura earthquake. A refurbished and fully tenanted building, so that the owner was really happy about that. They'd had to swallow quite a bitter pill in terms of the cost of the project. You know, we spent about $85 million of their money investing in this project. About a third of that, I think, was structural, and 2/3 were, you know, the dealing with that, the make good, the after hours work, with the complexity associated with that. So a lot of money, but they got a building that was refreshed, re-tenanted. It was undamaged after Kaikoura, and so they came out of it a lot happier than they certainly went into it. We learned a lot of lessons around design, assessment and strengthening techniques, and it was really a first in a lot of respects in terms of a building that was so challenging and so complex and so, you know, big to deal with, and we proved that we kind of could do a project of this scale, particularly with a building that was tenanted through the course of that work, overcoming some immense technical and logistical challenges. And it's really pleasing at the end of it for the project to be recognised nationally and internationally. So just to kind of finish off, I just wanted to show some images. I mean, I really like some of these pictures that just show the people that had worked on the project during the course of it. It was really hard yards, a lot of night work, a lot of shift work, a lot of out of hours for all the noisy drilling and the like. You know, some interesting things happening along the way, like hitting perched water tables when they're doing some of the drilling. Yeah, a lot going on for a long, long time. It was a pretty unrelenting project. And I couldn't kind of do this talk without saying a big thanks to this guy here, so Joe White, who's now up in our Netherlands office, but he was a big part of this project through the design phase. And finally, you know, nice to get some recognition of this at the end. And I suppose something I'd like to kind of, you know, suggest to the rest of you about telling stories about the projects we do and kind of taking the time to write up these sorts of presentations and submit them for awards and talk about the fantastic things we do in the construction industry and the fantastic projects we get to work on. And I, you know, often don't think we talk about our projects enough and get the recognition we deserve for some of these projects. So that's a bit of a plug from me to you to kind of talk about the stuff that you're working on. You know, submit projects to conference presentations, and then you can start getting recognition in some of these magazines. So this is the Structural Engineer, the magazine of the Institute of Structural Engineers in the UK, and I'm not sure how many times they've had a New Zealand project feature on the front cover of their magazine. So that was pretty cool. Thank you.
Cool.